We'll move on then into talking about relative motion, a class of problems with linkages and whatnot. We're going to go back and use our relative motion equation. So if I start out, and I've got a diagram similar to what your author has, if I look at this link AB, and I look at it both rotating and translating, so I think you can see that the motion from here over to here has some translation in it, and it also has some rotation because this distance DRA and DRB is not the same. So if I break that up a little bit and look at it like this, and look at it, well, if I break up the translation and the rotation, so I take the translation and separate it and then add it to the rotation. Okay, so I've got the translation at this dotted one. If it were to just translate that, this would be DRA and DRA, and then I add the rotation to it, I can get to the same point, and that allows me to look at it a little bit easier. I can look at it piecewise. And in fact, I can look at this vector triangle that I have here, where I can say that DRA plus DRB with respect to A is equal to DRB. Or I could come up to my equation that I hinted at last time and that we've used before, that the position vector RB would be equal to the position vector RA plus the position vector B with respect to A. And then, of course, you differentiate that and you'd get the velocity, differentiating with respect to time, and then differentiating again with respect to time, and you get the acceleration. So, yes?
How would that be a triangle? Wouldn't it all be the same line?
Well, no, as it rotates through that, this angle in here, I agree, this angle here could be fairly small. But
that angle would change.
Right. So I mean, this line here is parallel to that line there. But as this rotates, let me argue from the extreme here. Let me take something like this and say that it rotates like that. Okay, so when it gets over here, it would have been at this point, and now you've got it up at this point, so you definitely have a triangle there, wouldn't you?
Yeah, definitely there, but where this picture is drawn, it shows that the B, position of B is still parallel to the position of A in that sense.
Well, the only way that would be possible, if from vertical this went halfway here and halfway over there. In that case, they would all be in a line. But the vectors can still all line up in a line. There's no requirement that they be in a triangle. Okay. Other questions? So we're going to use these equations. We'll first work with the velocity because it's probably a little easier than the acceleration. Acceleration can get a little bit ugly because we talk about the acceleration of A, and there's probably more to that than we might think about. That could have a normal piece, that could have a tangential piece. So those terms might rapidly expand on us. But looking at the velocity, let's go to an example. So I take this linkage example here. I've got a link here that's 100 millimeters going from O to A, and I've got a link here that's 75 millimeters going from C to B, and then I have this connecting link AB. Okay. And people might wonder, well, why would I have a three-link system like this? A three-link system is fairly common if you look at the relationship of a piston and a connecting rod and the throw on a crankshaft. You have essentially a three-link system. If you look at a lot of suspension systems, for independent suspension systems, you have a three-link system. So we see a lot of them. We want to be able to analyze them. And what we've got here, all the dimensions are in millimeters, and we're told that there is some omega here, angular velocity. Omega CB is equal to 2 radians per second. And what I'd like to do is I'd like to go ahead and take an XY coordinate system. So I'm going to take a right-hand coordinate system. If I say that this is X, and this is Y, I'll go ahead and take this as Z. Is that right-handed? Yeah, as you take the fingers of your right hand and go from X to Y, your thumb will point out of the page at Z. And what we'd like to do with this is we'd like to find the angular rate, the angular velocity of OA, that link there, and we'd like to find the angular velocity of the link AB. So we'll start with the the tool that we had on the last slide, which was the velocity of A is going to be equal to the velocity of B plus the velocity of A with respect to B. And I've changed the subscripts from what we saw on the last page, but I think those subscripts there will work better for this particular problem. So I'd like to talk about the position vector for A. So if I talk about RA, what's that going to be? If I were to draw a position vector here, like that, and say that that is RA, how could I define that? Would it be okay to say that that's 100 millimeters in the J direction? Going straight up, right? Okay. And then if I do the same thing for B. So what if I talk about this RB here? RB. What's that going to be? Minus 75 in the, should be in the I, shouldn't it? Should be in the X direction. So, okay. How about RA with respect to B? So A with respect to B is going to be this one. There is RA with respect to B. Well, it should have two components, right? I got to go from B over to here, which would be minus 175 in the I direction, and then that gets me to this point, and then I have to go up 50 plus 50 in the J direction. Is that okay? So I have some of the pieces here. I'm going to expand this out a little bit. The velocity of A, we know that in general, make a little box here, general. What do we say about the vector expression for velocity? We could say it was omega crossed with r, couldn't we? Isn't that what we had, omega crossed with r? So if I do this one, I could say that the velocity of A is going to be, and maybe I'll move this down, I have a little more room here. So the velocity of A is going to be omega OA crossed with RA. And I can set that equal to, the velocity of B would be omega CB crossed with, did I get that, omega B? I should have that as RB crossed with RB plus, what's the velocity of A with respect to B? That's going to be omega AB crossed with RAB. So I've got some of those pieces. One of the things that I should probably do is put this omega CB into a vector expression. We're given the magnitude and the direction here, but if I wanted to write that as a vector, I'd use the right-hand rule, wouldn't I? Take your right hand, put your fingers in the direction of that rotation, and your thumb is going to point out of the page. What's also pointing out of the page? The Z direction. So we know that this is really 2 in the K direction. Okay, is what that is. So let me go ahead and go through this. Omega OA, that's something that we're looking for, right? But why don't I go ahead and assume that it's going to be in the Z direction. Is that okay? So I'm going to say that I have omega OA in the K direction. I'll just assume positive Z. If I've assumed wrong, what will happen? I get a negative sign, don't I? But I'm going to assume that it's in the Z direction. I think we can recognize that. It'll be in an axis that's in or out of the page. And I'm going to cross this with RA. So we've got that. I'm going to cross that with 100J. And we'll set that equal to omega CB. Do we have that? Yeah, that's 2 in the K. And we're going to cross that with RB. Do we have RB? Yeah, minus 75 in the I. And we add that to omega AB. Omega AB is unknown also, but let's assume that it's in the Z direction. So I'll just say the magnitude omega AB in the K direction. If I have assumed that wrong, I'll get a negative sign. And we're crossing that with RAB, minus 175 in the I, plus 50 in the J. So it looks like with that equation that I have one equation with 2 unknowns, the unknowns omega OA and omega AB. But I really have 2 equations, don't I? I should have 2 equations when I get done with the crossing. So when I do the crossing, what does this turn out to be? Omega OA times 100. So I'll say that I have 100 omega OA. And then what's K crossed with J? Minus I. Good. Is equal to 2 times minus 75 would be minus 150. And then what's K crossed with I? J, positive J. And then I'm going to have omega AB crossed in the K crossed with 175. So I'll have minus 175. Omega AB, what's K crossed with I? J. And then I have this 50. So I'll have 50 omega AB. 50 omega AB, and I've got K crossed with J, which is what? Negative I? Did I get that right? Let me double check that. Yeah, I think we're okay. Questions that far? These problems can be a little tedious, but you inventory what you have, you put them into your equation, and then you go through the math. Well, if I look at the I's and the J's and the K's, I don't have K's to worry about yet. I'll say that I have minus 100 omega OA is equal to, anything else I, should be equal to minus 50 omega AB. That's one equation. The second equation is going to be to say that 0, because there's 0 J's over there, 0 is equal to minus 150 minus 175 omega AB. So I equate the I's and the J's. I then have 2 equations and 2 unknowns. With 2 equations and 2 unknowns, I can solve for omega AB, and I can solve for omega OA, and AB turns out to equal minus 6/7 radians per second, and OA turns out to be equal to minus 3/7 radians per second. So my guessing wasn't too good. Both of those are actually in the negative K direction, aren't they? Okay. Which probably makes sense. I think if this one were going down, you could recognize fairly easy that the velocity of A is to the right, and this one would go that way. And of course, the right-hand rule is going to put that into the page. So the omega AO should not surprise us being a negative number. Questions on that?
So the omega of OA is negative 3/7, but the omega to AO would be positive 3/7.
Oh, well, OA, I mean, this piece here from O to A is rotating like this. Okay. Whether you're looking at it from A or O, it has the same omega at every point, remember? Okay. Other questions on that? No. What's that? Yeah, there's a second way to do it. we'll talk about instantaneous center here. So we've talked about no-slip. We spent some time coming up with the math of no-slip and looking at a simple problem with a tire rolling along a surface and looking at the velocity at the center versus the velocity at the top. And I kept saying pretty soon we'll give up on calling it a point of no-slip, and we'll start calling it probably a better term, instantaneous center, or instantaneous center of zero velocity. So when someone comes along and they talk about IC, instantaneous center of zero velocity, this is what they're talking about. So let's say that we have a body that has a couple of velocities on it. They needn't be the same velocity, and they may not even be parallel. And what I'm going to do is I'm going to take a perpendicular from one velocity and a perpendicular from the other velocity, and where those perpendiculars intersect is the instantaneous center. And the nice thing about that is it will turn a complex problem of rotation and translation into a simple problem of simple rotation. So we could model this thing as simply rotating about that point. Over here, let's say that they're parallel. Where's the instantaneous center? Well, I drop a line that's at right angles to both of those, and we come back here. There's the instantaneous center. I could look at that as simply rotating about that point. How about these two? Well, have a perpendicular. We have a perpendicular. There is the instantaneous center. Get a new pen. So we've got the instantaneous center right here. Now there's some that come up that can be problematic. This one, for instance, if I have a perpendicular here and a perpendicular here, I might be lulled into thinking that this is the instantaneous center. But not if that's a rigid body. If that's a rigid body, this is going to try and tear apart there, right? So this would really be nonsense from our concerns. That can't happen with a rigid body. Okay. The other one that actually can happen and we'll bump into is if I take these and let's say that these are parallel. So if I look at this, and if I say that the velocity of A is equal to the velocity of B, so they're of the same magnitude, when I do this, these lines are essentially parallel, aren't they? So where do parallel lines meet? Do parallel lines meet? Yeah, they actually do. Instantaneous center at where? Infinity. Okay? So my instantaneous center is at infinity, so I could say that omega is equal to the velocity divided by the distance, r. What would r be? Infinity, so what's omega? 0. So that's a simple example of translation. Okay? If your instantaneous center is at infinity, if these two lines are perpendicular, you know you have simple translation. Okay? So that's quite possible. It happens all the time, but is a little confusing when we think about the instantaneous center. Before we get all upset about an instantaneous center at infinity, we're really not going to be using the instantaneous center on this, are we? We're going to use simple translation on that one. But the instantaneous center can be very powerful on problems like this that turns complex combinations of translation and rotation into simple rotation about some point. And there's no requirement, as you can see, that the instantaneous center be on the body. Questions with that? Well, let's go back to the previous problem that we had and see if we can do this with the instantaneous center. I think you'll see that it's quite a bit easier with the instantaneous center, but before we give up on the vector approach altogether, is we need good practice with the vector approach because there is no instantaneous center of acceleration. So remember, it's always instantaneous center of velocity. When we start talking about relative acceleration, we're not going to have a shortcut tool like this. So it's good for us to get practice with the vectors because we're going to be forced into them when we talk about the acceleration. So I've got the same problem that I had before, exactly the same, and I'm going to see if I can do this with an instantaneous center. So I think what I'll do is I'm going to draw the instantaneous center for this link AB. And a lot of times that's half the battle, is figuring out what you want to draw the instantaneous center of. And if this omega CB is going like this, I don't think it takes much imagination or intuition to recognize the velocity of B is going to look something like that. It's going to be down, right? So let me put that here. There's the velocity of B. Okay? And if that's doing that, I think you can probably see, hopefully see, the velocity of A is going to go something like that, isn't it? Because as this pulls this down, this is going to be on a path like this. And I think it's going to have to move to the right. So if I do that, I could say that I have the velocity of A. Okay, if you don't like to make those jumps, go back and do the vector approach. We didn't have to do anything there. We just, only thing we assumed was K, and you saw it worked out even though I assumed K wrong. Well, let's see, where's the instantaneous center? I take a perpendicular here, and I take a perpendicular here. There it is, right there. That's the instantaneous center. Sometimes from a geometry point, it's nice to come back and try and find this here. There would be the instantaneous center right there. Not necessarily on that link OA, but on the space represented by this point right here. Okay, so that's our instantaneous center. Let's see if we can document this a little bit. What distances do I have here? I think I have 175 millimeters there. I think I have 50 millimeters there. As far as the velocity of B, I could say that that would be equal to omega CB times the distance from B to C, right? R of B. So do we have CB? Yeah, we got 2 times what's our distance there? 75. So that gives me 150, and that would be millimeters per second. Millimeters per second. So that's the velocity of B. So I could talk about this thing having some omega. We could really name that omega AB. So we could say that omega AB, that would be equal to the velocity at B that we just found divided by that 175, right? Because we know that velocity is equal to what? Omega times R? Or omega is equal to velocity divided by R. Okay, so I take my velocity and I divide by my distance, so omega AB turns out to be equal to 150 that we got over here, divided by 175, which is going to give me what? 6/7 radians per second. Okay. Now, we didn't come up with a negative sign, but remember, we got the negative sign because we had assumed that this was rotating this way in the previous problem, right? To get a positive K, I had assumed that it was going this way, and our negative sign said it really wasn't. It was rotating this way, which is the way that that's going, right? Okay, so we really have the same answer there. Then what if I want omega OA? Well, let me talk about the velocity of A. I could say that that's equal to omega AB times what, 50, the distance? Do I have omega AB? Yeah, 6/7 times 50. I don't really need the velocity at A. I mean, that's an intermediate step, so I'll just leave it like that. I mean, you could go through the math if you want to. What I really want is I want to come over and look at a picture here. If these are pinned together, if this pin at A is going through both of these pieces, I really know that if I take the velocity of A that I just found here, right there, I can get this omega OA, can't I? So omega OA is going to be equal to the velocity at A, divided by what distance? That total distance there, which is 100, right? So I'm going to take 6/7 times 50 divided by 100, which I get 6/7 over 2, which would be 3/7 radians per second. Okay. And again, I don't get a negative sign because I've taken this like this. The reason that I got the negative sign and the other problem is I had assumed it like that. That was the way that I got that positive k, right? And it really wasn't that direction. So that's probably a lot faster. There's nothing wrong with the other method, and that's actually good practice because, like I said, when we get into acceleration, we're going to be forced into a vector approach each time. Questions with that? Yeah.
How did you decide the direction of the velocity at A?
The direction of the velocity at A?
Yeah.
How did I decide that? Well, I think you have to recognize that if this velocity is down, then this link is going to start to pull down the next. If we were to take another snapshot in time, that link will look like that. Was there another question over there? No, this is not. Well, this is, but this type of problem is not. If you go back to that question number 42 that I suggested you hold off till after the exam, it looks a little like this. Other questions? Let's try another problem using the instantaneous center. Can we come up with this problem, can I come up with the velocity at A, that point there, the velocity at D, that point there, and the omega AB, the angular rate of that link ADB? We should be able to. I mean, the question always comes up, why do we look at these linkages like this? Is this just something to trouble students with? Hopefully not. I mean, if you take a link like this and a link like this, and then we have a link here. Maybe we'll put a spindle on it. We'll put a tire on here. Probably better put a spring in here, huh? Okay. That'd be a lot like analyzing the suspension of an automobile, wouldn't it? Okay, so being able to come up with the acceleration, the velocity at different points, can be a powerful tool. So what link do you want to draw the instantaneous center for? How about this horizontal link right here? Would that work? Okay. So I'll do that here. And a lot of times it takes a little practice to figure out where you put it on your paper so you don't end up with lines running off onto the table. But that's okay. So this is A. And again, if we're given that this link is going like this, the velocity of B would be perpendicular to this, wouldn't it? There's the velocity of B at right angles to that. So let me put that on here. There's the velocity of B. That's going to be at right angles. So if I have a perpendicular here, we have that at 45 degrees here, right angle there. Then how about the velocity of A? If B is moving this way, A has to go to the right, or that link's going to tear in two. So let me put the velocity of A here. So that's the velocity of A. And I'll take a perpendicular there. Just got it on the page. So that's our instantaneous center. We can take this complex combination of translation and rotation and turn it into simple rotation about that point. Now, do I know more about the velocity of B? I think I should. Let me say again, the velocity is equal to omega times r, and omega then is equal to v divided by r. So this would be equal to what? There's our omega, 10, and what's our r? 6 times the square root of 2 by the geometry that's given. So I have 10 times 6 root 2. So that's the velocity of B. Let's see, if this is horizontal, this is also going to be 45 degrees, isn't it? This total distance is, 14 across here? 8 and 6 gives me 14. So what's this distance here? That should be 14 also, shouldn't it? I didn't do a real good drawing. If this is a right angle and this is 45. Okay, so this would be what? 14 times the square root of 2. So we oftentimes turn our vectors in for geometry, so we have to go through some geometry here. So this is point B. So what if I want to talk about omega AB? I could say that that's really omega AB, isn't it? So what's omega AB equal to? Well, velocity divided by distance, right? Do I have a velocity over here? Yeah, I do. 10 times 6 root 2. Do I have a distance? Yeah, 14 root 2. So I get to cancel the root 2's and I come up with 4.3 radians per second. So that's omega AB. I got that. What else do we want? We want the velocity at A. Can we get the velocity at A? Sure. The velocity of A is going to be equal to some omega. Why don't we take this omega here? 4.3 times the distance. What distance are we going to have? 14? Yeah. So I'm going to multiply this by 14. I think I will divide by 12 for the units. So when this turns out, I get 5 feet per second. If you didn't divide by 12, you'd have 60 inches per second. That's okay, but I'll leave it like that. So that's the velocity at A. How about the velocity at D? Where's D? Right there, isn't it? So we do this to show you how easy this is. Again, going from my instantaneous center, I draw a line from the instantaneous center to that point D. And then where do I know my velocity is? Perpendicular to that. There's the velocity of D, isn't it? Okay. So now it becomes a simple matter of getting that distance. Okay. So what's that distance equal to? Yeah, the square root of, what's this side? 14 squared plus what's this side over here? 6 squared, which gives me, what, 15.23 inches. Okay, so that's the distance. So now I can say the velocity of D, very much like I did with the velocity of A, is simply 4.3, because that's the angular rate, that's omega. And here I'm going to multiply by 15.23. And again, I'll divide by 12 for the units. And we'll come up with 5.44 feet per second. And if we wanted to figure out that in a vector form, we could come in and find this angle in here with geometry and whatnot too. Questions with that? Everyone's good? Makes the problems fairly easy. The last thing I'll mention on this is you can really take this to more extremes. Let's say that we have a problem where we've got some sort of a slider here where this is constrained in a track. And maybe we have a slider here where this is constrained in some track. And then we have this arm that's attaching these together. Like this, and maybe we extend this way out here. An example of this, I mean, until I drew this extension out here, would be a panel in a garage door, right? And if we had this like this, as you look at opening or closing a garage door and that going around a corner, that's exactly what you have, right? Okay. Well, the reason I put this on out there is, let's say that you're told that this has some velocity here. You're given that velocity. So if we take that velocity, we could say there's our perpendicular. I think we would conclude that this has to be going that way, right? It's hard for the panels on the garage door, one end going up, one end going down. That doesn't happen in this world, right? Unless it breaks. Still doing rigid bodies here. So this is perpendicular, so this becomes our instantaneous center. Well, some joker comes along and wants to know what's going on out here. What can you do? I mean, in the previous problem, we asked what was going on there. I just want you to realize that it doesn't have to be between those points. You can take this thing, you come back here with your instantaneous center, and what do we know? There's our velocity there, right? So if they give you the dimensions, you can figure out the geometry and you can figure that out. So this is a very powerful tool. It makes problems go very quick and very easy. The one thing that we're going to have to be careful of is we're going to have to be careful that we don't overuse it, because when we get into the problem, for instance, that the acceleration of A is equal to the acceleration of B plus the acceleration of A with respect to B, there is no instantaneous center of zero acceleration. So we're not going to want to use it on an acceleration problem. However, a lot of times if we have some normal acceleration, isn't normal acceleration a function of omega? Yeah, so we'll end up coming back and probably using this to get an omega value, but we will not use it directly on the acceleration. So use it to your advantage, but don't overuse it where you can't. We'll continue on with that in the next lecture. Take care.